Hello and welcome back to Chapter 1. Today we're going to look at Section 5, which deals with infinite limits. When we are done with Section 5, you should be able to determine what an infinite limit is from the left and from the right, and be able to not only find but sketch vertical asymptotes as well. I'd kind of like to start out by looking at a discussion, and you do not have to write this stuff down. This is just kind of so that we know what an infinite limit looks like and is and whatnot. But if you look at either a table or a graph of this function here, which is f of x equals 3 divided by x minus 2, what you'll see is that as f of x actually increases without bound and decreases. So I'm increasing as I get closer and closer to this asymptote, and I'm decreasing as I'm coming in from this direction as I get closer and closer to this asymptote. Now, as we increase and decrease without bound means we're approaching either an infinity or a negative infinity. So if we write this out, let's look at from the left. So I have the limit as x approaches, and it looks like my vertical asymptote is here at 2. So as the limit as x approaches 2 from the left of 3 divided by x minus 2 is going to be, as I get closer and closer to 2, it looks like I'm approaching a negative infinity. So I'm going to write a negative infinity. And when I look at the limit as h approaches 2 from the right of 3 divided by x minus 2, I notice that as I get closer and closer here, I'm increasing without bound or approaching a positive infinity. Now, an infinite limit is actually where we take a limit, and as f of x increases or decreases without bound, as x approaches c, this is an infinite limit. So these right here are cases of infinite limits. We're increasing or decreasing without bound. So the limit where f of x increases or decreases without bounds as x approaches c, this is called your infinite limit. Okay, that's what we're dealing with in this section. Now your book gives you this nice big definition as you're going to look at right here. The thing I really want you to know is that the limit as x approaches c of f of x equals infinity, or the limit as x approaches c of f of x equals a negative infinity. And when you see that, when you take a limit and you're approaching either that positive or negative infinity, you should know that you're getting a function that's going to increase or decrease without bound. And because a function is increasing or decreasing without bound, if you recall, before we said that that limit did not exist. And even though we're finding the limit and we're saying that's equal infinity, it doesn't necessarily mean that the limit exists, okay? Because we proved before that if we have a limit that increases or decreases without bound, it doesn't exist. So the infinite limit actually tells us how it fails to exist by noting that we have that unbound behavior. Now if we look at example 1, it says determine the limit of each function as x approaches 1 from the left and from the right. So in this case, if I look at A, the limit as x approaches 1 from the left of f of x, so let's look at what's going on as we're coming in from the left. It looks like we are increasing without bound in the positive direction. So I'm going to say that this equals infinity. Likewise, as I look at the limit, I have to move this up here, as x approaches 1 from the right of f of x, okay, my function is still increasing without bound, so I'm going to say that this also equals a positive infinity. And that's okay, we can do that. Now if I look at part B, and I look at the left-hand limit, or as x approaches 1 from the left of f of x, I notice that my function is getting closer and closer to the 1, but it's still increasing without bound, which means that we have a positive infinity. Likewise, the limit as x approaches 1 from the right of f of x, this here equals, and if we look at our function, it's decreasing without bound, so this would be a negative infinity. When we are looking at functions that increase or decrease without bounds, a lot of times we're going to be running into vertical asymptotes. And if it were possible to extend your graphs, you would see that your graph becomes arbitrarily close to but does not actually touch the function itself. Okay, and if you recall, that pretty much is the definition of a vertical asymptote. And vertical asymptotes are these dashed blue lines that we know that our function gets close to but does not actually cross. So your theorem, or I'm sorry, the definition of a vertical asymptote says as f of x approaches infinity or negative infinity, as x approaches c from the right or the left, then we say the line x equals c is a vertical asymptote. Because remember, your function's undefined there. Okay, and theorem 1.14 says that if f and g are continuous on an open interval that contains c, and f of c is not equal to 0, but g of c does equal 0, then there's an open interval that contains c where your function g of x is not equal to 0. Okay, so it kind of gives you something like this right here. Oops. Okay, and we know that we have a vertical asymptote at x equals c. Now, this here is only true, okay, or I guess it requires, maybe we should say. So this theorem requires that the numerator, okay, and remember that this here is really a rational function, so it requires that your numerator at x equals c is a non-zero number. Okay, because if it's not a non-zero number, or if it is 0, then you're going to end up with 0 divided by 0, which is the indeterminate form, and you can't have that. So example 2 says to determine the vertical asymptotes of each graph, and from pre-calc, I hope you remember that you calculate your vertical asymptotes based upon what makes the function undefined. And in this case, or in all cases, if you have a denominator, we're going to just take that denominator and set it equal to 0. So for part A, if I take 2 times the quantity of x plus 1 and set it equal to 0, I know that x then is equal to a negative 1. So this implies that I have a vertical asymptote at x equals negative 1. Okay, and I'm going to do the same thing for B. This right here is where my function will become undefined if I plug in the correct number. To find out what that number is, where my vertical asymptote exists, I'm going to take, and I'm going to factor that because I see it's a difference of 2 squares. So now I have x minus 1 times x plus 1. Set that equal to 0. And this is going to tell me then that my vertical asymptotes are going to occur when x is equal to plus or minus 1. And last but not least, I have cotangent, and my favorite thing to do with a function like that is to put it in terms of sines and cosines. So cotangent is when I have cosine of x divided by the sine of x. So I now need to go in and look at when my denominator, or sine x, is equal to 0. And hopefully you remember that that occurs at increments of pi n, or pi. So that tells me that x is going to equal to, or be equal to pi. And I'm going to put an n here because our trig functions are periodic, or they're repetitive, it's going to be every increment of pi. So graphically, let's just confirm our answer. We said that we had a vertical asymptote at x equals negative 1. I see I have a vertical asymptote. Again, my function is increasing without bound from the right, decreasing without bound from the left. So I have that vertical asymptote. Part B, I came up with plus or minus 1. So I have those vertical asymptotes here. I have, looks like I'm approaching infinity as I come in from the left and from the right. And then C, it looks like at every increment of pi, I have 1 pi, 2 pi, a negative 1 pi, negative 2 pi, and so on. I'm having these, my function is increasing or decreasing without bound on either side, or approaching a positive negative infinity. So again, I have vertical asymptotes there. Okay, and the last thing we're going to look at are our properties of our infinite limits. Okay, and this is kind of similar to what we've been seeing. if you're taking the limit as x approaches c of f of x and you get infinity, and we're taking a limit as x approaches c of a different function, we actually get a numerical limit, then we have a property that's called the sum or difference property, and all that says is as we're taking the limit of a function that approaches infinity, that equals infinity, and the limit of g of x equals a limit, we're really going to be adding two functions that give us a limit of infinity. And that's because you're adding infinity to some number. Well, infinity is going to override that number. Same thing with a product. If I have infinity for the limit on f of x and a number on g of x, that infinity is going to override or overpower that number. So again, I'm going to get infinity or negative infinity if f of x was negative infinity. Now for our quotient, g of x is going to be a number, f of x is going to be infinity. So if I take any number and I divide it by an incredibly large number or infinity, then that's going to give me 0. Because think about like 1 divided by 1,000,000, okay? That's going to give you a really small number. So if I take like 1 divided by infinity, which is an even bigger number, that's going to be approaching 0 as well. So example 5 says that we're going to determine the limits, and I'm given that the limit as x approaches 0 of 1 is equal to 1, so this is one function, and the limit as x approaches 0 of 1 divided by x squared is equal to infinity. So if I want to add these functions, and I take the limit as x approaches 0 of 1 plus 1 divided by x squared, okay, I'm adding 1 to infinity essentially, and 1 plus infinity is going to give me infinity. Same thing with b. If I take the limit as x approaches 1 from the left of, and now I'm going to divide these out, I have x squared plus 1 divided by my cotangent of pi x. So what this really means, if I plug in the limit for x squared plus 1, this is going to give me 2 divided by a negative infinity, and anything divided by a really, really large number, even if it is negative, is still going to give us 0. And likewise for part C, if I wanted to find the limit as x approaches 0 of the product of 3 and the cotangent of x, this is really, my limit for 3 was 3, and I'm going to multiply that by infinity. Well, 3 times infinity is infinity itself. And your fun facts today is a list of randomness from anengineeraspect.blogspot.com. Did you know that 93% of all greeting cards are purchased by women? And approximately 10.5 gallons of water is used in a dishwasher. However, when you wash dishes by hand, you can use up to 20 gallons. The average lifespan of an American dollar bill is 18 months. There's approximately 60% of the water that's used in households during the summer is actually used for watering flowers and lawns, not for human consumption. The typical lead pencil can draw a line that is 35 miles long. There are approximately 18 billion disposable diapers that end up in landfills each year, which I'm guilty of, and these diapers can take up to 500 years to fully decompose. Bamboo plants can grow up to 36 inches in a day, and did you know that if you bought a new refrigerator, unpacked it, plugged it in, but left the refrigerator door open, it would actually heat up your room, not cool it down? And that is due to the fact that a refrigerator is a heat pump, and it actually moves heat out of the refrigerator to the room. So with that, my friends, you are now fully informed of some random fun facts. And have a good day.